All right, we want to talk through the multiple choice on the simple harmonic motion universal gravitation test. So, starting off here, I'll work it on separate paper. This first one says, hey, a simple pendulum of length L, whose bob has mass m, oscillates with the period t. If the bob is replaced by one of mass 4m, then the period of the oscillation would be. And so for this, we want you to say, well, um, I know, or I see on the AP formula sheet, that the period of oscillation for a pendulum, you're like, hey, that's T is 2 pi root L over G. And you say, so we're going to take this pendulum and we're going to change the mass, make the mass 4 times bigger. What does that do to the period? You say, well, we're not changing the length. We're not changing the gravitational field strength. So the T should be the same. So the period should still be T. So that should be C. 2. Which of the following is true for a system consisting of a mass oscillating at the end of an ideal spring? And you say, well, if I've got this mass on the spring and it's oscillating back and forth, right? Then you say, hey, I know it's whipping between these three positions. Well, all these positions, but there's like a spot in the middle and it's going back and forth. And you say, well, I know that as it goes back and forth, saying, hey, the kinetic and potential energy is equal at all times. So like, no, it's going to be changing speeds as it goes and changing crush length on that spring. So they're changing all the time, the energies. The kinetic potential energies are constant. No, they're changing all the time. Maximum potentials when the mass goes to equilibrium, like no. When it's at equilibrium position here, that's when there's no potential energy. And in fact, our kinetic energy would be maximum there. And then when it's crushed all the way or stretched all the way, that's when the potential is at maximum and the kinetic is zero. So basically the answer we want here is D. The maximum kinetic and maximum potential energy are equal, but they occur at different times. So D is the one we want. 3. The mass of planet X is 1/10 that of the Earth, and its diameter is 1/2 that of Earth. The acceleration due to gravity at the surface of planet X is most nearly. So for this one, we're thinking about the acceleration due to gravity. So when I'm standing on this planet, and you say, well, hey, my acceleration due to gravity, that's going to be little g, right? And so the way that I usually think about that is sigma F equals ma. The acceleration due to gravity means the acceleration if the only force acting was gravity. So I would just have gravitational force is ma, and that acceleration we call little g. I use my Newton's law of universal gravitation. I've got big G, mass of the planet, mass of the object over that distance between their middles squared. Well, if I'm at the surface of the planet, then that's just the radius of the planet that I'll be squaring there. Mass of the object times G. Mass of the object drops out. My acceleration is going to be G, mass of the planet over that distance from the center squared. Now, what we're doing is we're making some changes. It says, hey, comparing to Earth, this has 1/10 the mass the planet does. So I'd have like 1/10 the mass. And they say the planet has 1/2 the diameter, so it would have 1/2 the radius. Instead of squaring an r, I'd be squaring an r that's half as big. So what has happened on this side to keep them equal? We're not changing big G. So to keep these sides equal, little g has to change. Well, I've got 1/10 over 1/2, and that half is going to be squared. So that's like 1/10 divided by 1/4, or that'll be 4/10. So my new acceleration of gravity is going to be 4/10 of g. Rounding 9.8 off to 10, 4/10 of 10 would be 4 meters per second squared. So it'll be about 4 meters per second squared, and that is choice B. Question 4. They give us this graph, and notice it's a graph of position versus time. And they say a particle moves in simple harmonic motion represented by the graph above. Which of the following represents the velocity as a function of time? So from the position graph, I want to draw the velocity graph and get the equation. So you're going to say, well, what I do is I just said, let me just write the equation for this graph and then take the derivative. So I said, okay, so this is going to be, I'm going to use the basic formula for a trig function. Now look, this is starting at its maximum and then going down the minimum. So this is be best to use a cosine function to represent this because cosine starts at max. So I'm looking at like a cosine omega t plus v sort of thing, right? I'm going to say, okay, so my position graph here, my amplitude is 4. And then you say, now what about the period? I can see this one goes through a cycle in 2. Now, things are supposed to go through a cycle in 2 pi for a trig function, but it's going to be divided by that omega in front that modifies it. And so you say, well, look, my period here is actually 2. Let me rearrange this. Omega would be 2 pi over the period. In this case, my period is 2. So 2 over 2, my omega is pi. So this is going to be pi t. And then I don't have a phase shift. This cosine's starting at its maximum. So this is my function for position, but they don't want the position equation. They want the velocity equation. So now I take my derivative. Derivative of sine is cosine, derivative of cosine is negative sine. This would be negative sine of pi t. But and when I do that derivative, I've got a nested function. So I've got to multiply by the derivative of that nested function using the chain rule. Derivative of pi t is pi, so it's going to kick a pi out in front. So I'm going to have my velocity being negative 4 pi sine pi t, and that is choice E, negative 4 pi sine pi t. Okay, question 5. A ball is dropped from a height of 10 meters onto a hard surface, so the collision surface can be considered elastic. Under such conditions, motion of the ball is okay. So we're dropping this ball above a hard surface. When I drop it, it starts with speed of 0 and goes faster, faster, faster. And then it's going to slam into the ground. Now, they tell us they want us to consider this collision to be elastic. And so you might remember elastic means the kinetic energy before equals kinetic energy after. But this is one of these special case collisions we're supposed to know when one of the things is hugely massive compared to the other. That we consider to have happened is that this thing's going to rebound with as much kinetic energy as it came in at. So the speed here is going to be equal and opposite the speed when it hit the ground. So it would bounce back up to the same height, right? So as it goes up, it would get slower, 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 and end at the same height. So this thing would go bounce, 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 bounce. So it's a repeated motion. It's cyclic. However, is it simple harmonic? Well, the definition of simple harmonic is that the system is affected by a force that is a restoring force that's linear with respect to displacement. Well, in this case, as this thing falls, that force is more or less a constant gravitational force. And then when it gets to the bottom, there's this sudden bam force. This is not going to be a simple harmonic oscillator. It is not going to be choices A, B, C that say they're simple harmonic. E says a motion with constant momentum. Like, no, the momentum is going to change when this outside force from the ground shoves on it. It goes from momentum down to momentum up. So really, D is the only one that it could possibly be. D says it's periodic. Okay, it's repeating with a period of about 2.8, but not simple harmonic. I'm not even going to do the calculation to see if the period is 2.8. If it takes 1.4 seconds to get to the ground. Uh, it's the only possible choice. It must calculate out to be that way. So D is the answer we want for that one. Falls from 10 meters. Yeah, it's going to take more than a second. Alrighty. That's the first 5 problems. Continue on problem 6. A particle moves in a circle in such a way that the x and y coordinates of its motion are given in meters as function of time t by these functions. X is 5 cosine 3t, y is 5 sine 3t. So this is that whole business of I've got something that is moving around in a circle. Now, we are of course very familiar with the idea of the unit circle. And we know if I have something moving along here, right, as it goes along, goes along, goes along. If you like kind of measure an angle, if this was a unit circle with a radius 1, we remember that the horizontal piece here, horizontal position would be given by cosine of this angle, and the vertical piece would be sine of this angle, that angle theta. So when I'm writing the equations for a circle, I could say that its x position is given by, now if it was a unit circle, it would just be equal to cosine of theta, right? And my y would be equal to sine of theta. But You say this does not have a radius of 1, then this has a coefficient of 5. Maybe it's a circle of radius 5. Then I would have 5s here. And then instead of saying theta, they're giving me a function of time. Well, I could go ahead, I could rewrite this. I could say, using my rotational motion things, I can say, hey, let's talk about theta as a function of time. If I was going at a constant speed, then just like we can say x equals vt, I can say that my angle would be omega t, right? So I might write this equation as 5 cosine of omega t, right? And that would be an equation for this thing going around a circle. That would be its x position, and its y position would be 5 sine of omega t. Now, in this case, it looks like omega is 3. Okay, so this thing's going around a circle at a constant speed, as it turns out, because I see I've got the same coefficient, same, yeah, sorry, coefficient on the t. I was going to say same omegas there. Okay, good enough. 6. So something we know is that if something's going in a circle at uniform circular motion, we know that its x coordinate, x position, and y position basically oscillate like simple harmonic oscillators, is something that we saw from a MECU episode, actually. 6. What's the period of revolution, the time it takes to go around? Well, if the omega is 3, we know that the period of a sinusoidal function is 2 pi over that omega. So 2 pi over 3, so 2/3 pi, and that would be choice C. Which is true of the speed of the particle? Well, um, I can go ahead and I can find the speed by taking the derivatives of the positions with respect to time. If I did that, like the omega would kick out in front when I take the derivative. So I'm going to have 5 times that omega, so 5 times that 3. So 15 will be my coefficient. So like my x velocity would be, derivative cosine is negative sine, would be negative, I would kick a 3 out, 3 times 5, 15 sine of 3t. And then my v and the y would be like a negative 15 cosine of 3t. And so the thing about these is as I'm going around, when I'm here, say, my velocity is like this. When I'm here, my velocity is like this. When I'm here, my velocity is like this, and so on. The point is that, like, say when I'm here, I notice that my x velocity is 0 at that instant. I'm going just straight up my velocity here. And so you say, hey, well, this happens to be when the x is maximum, right? It's when the y velocity is maximum, the x velocity is 0. And so you're like, hey, and then here, when I'm at this point, that's when my vertical velocity is 0, my horizontal is maximum. Well, the maximum is just the coefficient, right? Because these are sine functions, the biggest value is 1. So my biggest value I'm going to get is 15, right? So, and when the one is 15, the other one's 0. So 15 is the speed as this goes around on constant speed. They've got, we're all good here. So it's always equal to 15, my speed. All right, 8. A satellite travels around the sun in an elliptical orbit as shown. As it travels from x to y, so we're going from the far point to the near point in the orbit. We're going from apoapsis to periapsis. You say, what's true about speed and angular momentum? Well, as I go in closer to the sun, I am losing gravitational potential energy, but we're gaining kinetic energy. So I should be getting faster as I head in from x to y. So the speed should increase. That would be choices B or D. I am down to a 50-50 chance. Now the question is, what happens to angular momentum? You say, well, angular momentum, the way you change angular momentum is by applying a torque. If I'm looking at this thing and I'm saying, hey, it's going around the sun, making the sun the axis of rotation, then we will recall that as this thing moves around, the only force acting is that gravitational force, but it's always pulling right along that r vector. And so if I tried to calculate a torque is r cross f, I want the part of the force that's perpendicular to the r vector. See what makes it twist? Well, there is no part perpendicular to the r vector. It's going parallel to the r vector, well, anti-parallel. I would have like a r times the gravitational force times the sine of 180. That's going to give me 0 torque, which means the way you change angular momentum is you apply a torque through a time, is the change in angular momentum. There's no torque. Angular momentum is constant. So we want speed increases, angular momentum is constant. That would be choice D. Question 9. The radius of the Earth is approximately 6,000 kilometers. The acceleration of an astronaut in a perfectly circular orbit 300 kilometers above Earth would be most nearly. Okay, now they want the acceleration. So again, we're going to do a sigma F as ma. Now, if I'm doing an orbit, right, around the Earth, a nice circular orbit, then you say, well, I just have my gravitational force is the only force on me pulling me into the center. That would be my mass times centripetal acceleration, right? And the centripetal acceleration is what we're trying to find. Now, I'm not going to solve that from v squared over r because I don't know what the v is. I'm going to solve it from the rest of this equation. Gravitational force is going to be big G, mass of the planet, mass of the satellite, over that distance squared. Now, the distance is going to be the radius of the Earth plus that extra 300 kilometers above. Now, if I was at the surface of the Earth, this would just be the radius of the Earth squared. And over here would be the mass of the satellite times that acceleration. That acceleration would be little g, right? Acceleration due to gravity. So this acceleration I'm trying to find is this. Now, instead of being at Earth's surface, though, I'm going to be what? 300 kilometers above. Now, normally it's 6,000 kilometers, and I'm now going to add 300 to that. Well, 300, that's like 600 would be a tenth. I'm adding 5% onto the height. So instead of having a radius of Earth squared in the bottom, I'm going to modify that by a factor of 1.05, 5% increase squared. I'm not changing G, not changing the mass of the planet. What's going to have to happen here? I'm going to have to multiply this by 1 over 1.05 squared. You're like, that's just going to decrease it by a little, right? So looking at my choices here, it's not 0. It's not teeny tiny 0.05. It's not having it, right? From 9.8, it's not going to go up. It's got to be 9. It's the only option. It's going to decrease just a little bit from 9.8 down to 9 when I go there. We could do the math, put the numbers in my calculator and check, but that's the only reasonable answer. It's got to be D. And then question 10. Question 10 says, I've got a small mass released from rest a very great distance from a large stationary mass. Which of the following graphs best represents the gravitational potential energy as a function of time? So I might imagine here is my great big mass, right? Like a planet or something, large stationary mass. And I'm going to release this little mass from way out there. What's going to happen over time? Well, it's going to start to fall in faster, 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 faster as it comes in, right? Now, I am asked, what does the potential energy versus time graph look like, right? So I'm trying to find potential energy versus time. Now, we remember that potential energy is always negative. The formula for gravitational potential energy is negative G m1 m2 over r. So energy versus position is a 1 over r type curve. So if I had a graph of potential energy versus position, that gives me this as a negative 1 over r graph. It gives me a graph shaped like this. But they don't want potential energy position, they want potential energy in time. So what's going on? I'm starting off a very great distance away. So at time 0, my potential energy, at infinity, it would be 0. So my potential energy is starting near 0. Okay, if I was at infinity, it would be 0. And now I'm going to slowly fall in closer, closer. So as time goes by, I'm actually getting closer in this way. So on this graph, I'm starting with my energy out here. I'm starting out far away. And then as I get in closer, closer as time goes on, my potential energy is going to go down. So as I'm going this way with time, the energy is going down like this. So the energy's got to go downward. Now, looking at my options, as time goes by, I only have two graphs that are going downward. One of them is a linear, and one of them is some sort of a curve. And so you're like, well, as I go in, I'm getting faster. And so that means I'm going to go farther and farther each bit. Well, if this was straight, well, let's not even ask that way. So the point is, I'm going to drop more and more in each successive time interval because I'm going faster. So I'm going to go farther each chunk of time. So this graph's going to go down. But then also this graph curves down quicker. So definitely each chunk of time, I'm going to drop like more and more and more than I did before. So this graph is this is not going to be a linear. It's going to be going steeper. So the best option here, the only real option here is D. Okay. Questions 11 and 12. Question 11 says, hey, here is a graph of displacement versus time for something in subharmonic motion. You say, yeah, look, I can see it starting at the equilibrium position, going up, coming back, going up, coming back, and forth. Which of the following would show the kinetic energy as a function of time? And so you say, well, if this is the position equation, right? You say, hey, I know that I'm going fastest when I'm at the equilibrium positions. Look, I can also see that's the slope of this. I've got a really steep slope here, steep slope here. I got a zero slope here, zero slope here. So my velocity time graph, I'm gonna be going fastest here. Sorry, zero's velocity there and fastest here. And here I've got a zero velocity again. Here I had a really steep negative velocity, right? So I know that this is going to be a sinusoid like this, right? This is my, right? Again, if this is sine, this is cosine is the derivative. But I want kinetic energy, and kinetic energy is 1/2 mv squared. So I want to take this graph. The magnitude is going to get modified, the amplitude, but who cares? M's a constant. You see, what matters here is that v squared for the shape of it. So when I square this, this is going to get, maybe a little bit steeper of a curve. It's going to be 0, but then because I'm squaring, the negatives are going to pop up and be positive. So I need to do what a graph of, since v is a cosine function here, I need to see what a graph of cosine t, well, cosine squared of t, you know what I mean? I need to see what that graph looks like. And what that graph ends up looking like then, you're saying, look, I'm going to have my max, it's going to end up kind of curving and coming up and curving and coming up. It's going to be like looking kind of like that. Okay, because it's going to flip up when I go to do kinetic energy. So looking at that, you say, hey, I got to have my maxima at 0 and pi and so on. You say, hey, that's going to match this one. Where this one has a 0, this one's got a max. 0 position for maximum velocity. B is the one we want. Right? Okay, and then 12, which of these graphs shows kinetic energy as a function of displacement now? As this thing oscillates back and forth and back and forth, how's the kinetic energy change? Well, when my oscillator's at its limit, that's where it's changing directions, so that's when the speed is 0. So this graph is upside down. This is the one we need. I got to have minimum kinetic energy at the extremes and maximum when I'm whipping through the equilibrium position. This is the only one that's got a maximum at equilibrium, actually. So C is the one we want. And that's the multiple choice.